I'm talking about gap codes. You're not supposed to know what they are already. But if you search for them on the internet right now, you will find a whole bunch of coupon codes for the gap. Okay, but yeah, okay. This joint work with Mrinal Kumar, who's here, and Harsha, my student. Okay, so these are error correcting codes, which are based on evaluations of multivariate polynomials. Okay, and so I'm going to set up our favorite usual multivariate polynomial evaluation codes, which are Reed-Muller codes. So let's talk about Reed-Muller codes. Okay, and I'm talking about them not in the same setting as Lalita was, which was over F2. I'm talking about Reed-Muller codes over large fields, FQ, and this will be in the setting where they will have constant rate and constant relative distance. So we're looking at FQ. We think of Q as big. We'll take M, which is the number of variables. This is going to be a constant. And we will look at FQ to the M and evaluate polynomials of degree D, which will be something like 0.9 M, sorry, 0.9 Q. This is the kind of setting that we're working with. And these codes, let me say some basic things about them. We have to, because of the Schwartz-Zippel lemma, polynomials of degree 0.9 Q, when evaluated in all of FQ to the M, any two can agree on at most 0.9 fraction of the points in the space, and therefore they have relative distance 0.1. And they also have, and we can also talk about their rate. What's their rate? So the rate is the dimension of the space of polynomials of degree at most D divided by the total length of the code, which is FQ, which is Q to the M. This is the number of monomials of degree at most D in M variables. This is D plus M choose M. D plus M choose M over Q to the M, which is about, in our setting, 0.9, M is constant, so it's 0.9 Q whole to the M divided by M factorial. And down there is this. So what we get is 1 over M factorial times 0.9 to the M. Okay, and so the question that we started off studying was, so observe here that Reed-Muller codes in M variables can only give you rates which are at most 1 over M factorial. You cannot get a high rate code out of Reed-Muller codes this way. And the question is, can we get a high rate code by evaluating multivariate polynomials at a nice set of points? This is what the question is. So question, find a subset S of FQ to the M so that the rate can approach 1 while still having relative distance positive. So omega 1. Okay, so this was the question that we set out to solve, and we solve it, and we produce, I mean, we have some general solutions, and we also have 2 specific families that have nice, interesting properties. One of them is called cap codes, and the other is called gap codes. They stand for something, but that's not important. Not necessarily. We're happy with an evaluation domain contained within FQ to the M with this rate. And if you do product sets, the exact same Schwartz-Zippel calculation will hold, and you cannot really beat. Good question. AG codes do not provide an answer to this question because the way the question is formulated. I said, let us take polynomials of degree at most D and evaluate them on all points. AG codes do answer this question in the following setting, where you take polynomials of degree at most D, except those that vanish formally on a particular curve, and then you only look at those. So there's this modding out by the defining curve of the equation, and that is an illegal operation in the definition of my problem. Okay, so here is FQ square. And when we evaluate polynomials of degree D, so what happens when m equals 2? There's a 1 over m factorial that's sitting there. No matter, as long as this degree is less than q, you have this 1 over m factorial sitting there. So the rates are always at most half. What we really need is a subset of points where we can evaluate it, where we can evaluate the same set of polynomials. And presumably the subset is going to be a sparse subset of FQ square, so that the rate goes all the way up to 1. So we basically need to find half the points in FQ square where this happens. Okay, and I can just tell you the answer in one line. These are called cap codes. That's it. If you evaluate degree D polynomials on this set, these are cap codes. And the fact, which is a variant of the Schwartz-Zippel lemma, which is that polynomials preserve constant fraction distance. Omega 1 distance, even on this set. Correct. So this didn't make sense. You take an arbitrary order and you just take any order here. It can be a different order there, and take ai comma aj, where I plus j is at most q. And this actually gives a whole family of constructions. You can consider sets like this, and there are sets like this that outperform. Okay, so I drew it weird, but there are sets like this which have better rate distance trade-offs than the diagonal. There are sets, better than the diagonal, better than the whole grid. So there's a whole space of possibilities to play with based on the shape of the evaluation domain that gives you some interesting trade-offs between rate and distance. And in particular, they can also let you approach rate 1. So these are cap codes, but I'm not going to talk about them now. I will talk about gap codes now. The gap codes is a different construction, which also achieves very similar trade-offs, but they also come with extra properties. First of all, they're related to HDXs. So I will have the ability to say HDX in a talk for the first time, and which I've already done. And the second is they also are locally testable. So even though they are going to be a sparse subset of FQ to the M, they will still have enough local structure in there to test. Good. These are dense hitting sets for polynomials. These are in the setting of M being constant, and it's in the setting where we're not really caring about the seed length for this problem, but we're really caring about the size of the set, and we really care about lower order factors in that. So a good so maybe I can say it. Okay, I'll say it now. So one can consider this. Can take D and M arbitrary, both of them growing. And right, and then so in this case it's open to find S in FQ to the M with a size S being order of the dimension, which is D plus M choose M, such that so even within a constant rate codes are not known, such that the polynomials of degree D, so that polynomials preserve distance, so that relative distance is omega 1. And the best thing that we know for this problem is, this is a construction of Clivens and Spielman in the construction of constructing hitting sets for polynomials and the pseudo-random generator perspective. So you can have size S being D plus M choose M to the power constant. So this, I think, is a really, really nice open question, which we do not know how to solve. Our constructions will only be interesting when M is constant. At least, they will now only have positive relative distance when M is constant. Yeah. Questions? Yeah. Yes, the dimension of the space of polynomials is D plus M choose M. So you need at least D plus M choose M to even make sure everything is distinguishable. And the fact that it is achievable with order D plus M choose M is a simple application of probabilistic method. A random set of this size will do it. And in fact, it will even achieve rate plus distance approximately 1. Yes, in this setting, Q is growing. Yeah. Okay, so now I will give you the construction of gap codes. For the m equal to 2 setting, I can just define the set for you first, and then I will explain what's going on in a bit more. So S, we take S to be the following set. I want a set of size roughly half of FQ square. Here is a set of size roughly half of FQ square. You have to pause for 1 second to see that it's a size half of FQ square. Let A and B vary in FQ square and consider these points, A plus B, comma AB. There are Q square points apparently, but every point appears twice because it's symmetrical. The analogous construction when in 3 variables is the 3 elementary symmetric polynomials. A plus B plus C, AB plus BC plus CA, ABC. And fact, which the way I wrote it, it's not clear. And if you, I don't know, the way I wrote it is not clear. Fact, polynomials. Oh no, no, A and B are both elements. Yes, very good. Yes, thanks. So, wait, so now let's understand this again. So you take 2 elements of FQ, A plus B and A. Oh, cap was, you saw what I did. Oh no, they have the same rate and distance behavior. That doesn't mean they're the same set. Yeah, and in fact, they're not the same set because this will have some other geometric properties and the cap will not. They're solutions to the same problem. Yes, they're different solutions. So the facts is that polynomials of degree 0.9q have at most, vanish on at most 0.1 square fraction of S, which is a positive constant fraction. And this 0.9 and 0.1 are related by what's obvious. Okay, good. So let me say something more about why this is true. So actually, the set S looks like the following. So we have FQ square, and we have some lines on it. And lines L1, L2, up to LQ in general position. I'm not telling you what those lines are, but there are some lines, L1 up to LQ, which are in general position, which have the property that S is the set of pairwise intersections of elements of these lines. S is equal to such that this S is Li intersect Lj for I j contained in 1 to 3 up to Q. Okay, what are those lines? Okay, maybe it's obvious. Okay, I don't know if it's obvious, but okay. So there are some lines, and the definition of gap codes is really start with any lines in general position, look at their pairwise intersection points. There will be, if there were Q lines, there will be Q choose 2 intersection points. Evaluate polynomials of degree D at those intersection points. And whenever you take such a configuration, you get a theorem of this form. Polynomials of degree 0.9q cannot vanish on too many fractions. Yes, it should be Q plus 1. Q plus 1 choose 2 is Q choose 2, no? Oh, I see. Maybe A not equal to B. Let's do A not equal to B. Yeah. Then. Okay, so where do these sets come from? So both these sets, the diagonal half of FQ square and this set. Yes. 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 Any lines in general position. If you take so here is the so now I can just give you the general construction of gap codes in general. So gap codes in general. Okay, so we are in FQ to the M. We will take hyperplanes H1 etc. to HT hyperplanes in general position. T, and it's a parameter that will vary in my construction, H1 up to HT. Then we let S be the set of M-wise intersections of the HIs. So intersection of J in S, no, not S, J in J, where size of J equals M and J is a subset of 1 to 3 up to T. So we know that that intersection is a singleton. Correct. If you intersect I of them, you lose I in the dimension. And if you intersect M plus 1 of them, you get no points. This is the set S. So all M-wise intersections of distinct hyperplanes. And it should be clear that the size of S is T choose M. Because I took any T of them and took that intersection. And the claim about the distance is that polynomials of degree D can vanish on at most T minus D choose M points of S, a non-zero point. And that's yeah. And this is the analog of the Schwartz-Zippel statement that we need for such a code. Okay. So this is the construction. Questions about what it is? If you express the hyperplanes by equation, then what does the set look like? So if I take my favorite hyperplanes in general position, which are these van der Monde hyperplanes in general position, then the set will look like elementary symmetric polynomials in every coordinate. And yeah. Okay, and what is the asymptotics of of what the rate versus distance for these codes? I will just say that quickly. Right, so rate is D plus M choose M over T choose M. Relative distance is T minus D choose M over T choose M. So M is basically nothing compared to all this. So let's pretend this is D choose M and this is T minus D choose M. So if D equals rho times T, where rho is some scalar, then we're getting rate of rho to the M, right? And delta is 1 minus rho to the M. So this is the kind of behavior we get. So so just to summarize it fully, it's R to the 1 over M plus delta to the 1 over M equals 1. This is the trade-off that this construction is. And yeah, so and as I said, actually there are nice evaluation sets where r plus delta equals 1 basically. This is achieving something that degrades as m grows. That is something we hope will get fixed. And yeah, and these constructions are, I mean, maybe they're most interesting when m small. They are slicing down the diagonal. Yeah, in a symmetric way. You want a 1 over m factorial gain. So basically, in any tuple, only one out of all its permutations should be present, and you should do it in a geometrically consistent way. So it is a simplex, I guess. Okay, so I need to prove some things. I think. Yes. Yes. Can vanish. Oh, yes, good. So does not vanish on at least. Yes, thank you. On at least. Yes, thanks. Okay, so let me give a. So I will say the one fact that unites both these constructions. The fact that unites both these constructions is that the cap and the gap is that the set. So if S is an interpolating set for polynomials of degree t minus m, then any non-zero polynomial does not vanish or is non-zero at least t minus d choose m points of S. This is the fact that unites cap and gap codes. And I will say in one word or in one sentence how this is proved. If you have an interpolating set for polynomials of slightly larger degree, an interpolating set means any polynomial of this degree, whenever you have a function defined on that set, there is a polynomial of this degree that fits it, and there's exactly one such polynomial. For univariate polynomials, any subset of degree size is an interpolating set. But for multivariate polynomials, the choice, not any set can have this property. You have to choose them well. So if you take such an interpolating set, then it's automatically a robust interpolating set, meaning non-zero polynomials are slightly, any non-zero polynomial of degree D. Yeah, now non-zero polynomials of slightly lower degree automatically have many non-zeros. And the proof of it is basically one line. Suppose there was a non-zero polynomial of lower degree that had very few zeros, then by interpolation, you can find a polynomial that of very, very low degree that vanishes on those non-zero points. Take that and multiply it with your original polynomial, and you get a polynomial which vanished on your entire interpolating set of lower degree than the t minus d, which the t minus m that you started with. And this gives the proof of the distance. Okay, so but now I want to mention the HDX connection of these codes. So these are actually Tanner codes on the complete m-dimensional complex. Okay, so how does this work? So we'll have here h1, etc. up to ht. Okay, and these will correspond to the singletons. Then up above, you can have hi intersect hj. These will be doubletons all the way up to hi1 intersect him. And okay, so at this level, we have the codimension 1 spaces, codimension 2, and all the way up to codimension m. Yes. It's the same H's, yes. We started with arbitrary hyperplanes in general position, and we took various intersections. So if you take m-wise intersections, you get the evaluation set of our gap codes. But if you take m-1 dimensional, m-1 wise intersections, what you'll get is a bunch of lines. And each of these lines will contain lots of points. Why? Let's take h1 up to hm-1. You can take that and intersect with any of the other hj's, and you will get one of the points of your set. So inside this set S, there are many, many lines of points, collinear points sitting inside it. These collinear points are the basis of a local test. So, so let me quickly give a statement of this. So this is, I guess, a local characterization first. A function from S, so for gap codes, a function from S to FQ is a code word, which is the same as the evaluation table of a degree D polynomial. If and only if for all lines contained in S, which are the lines? So for all m-1 wise intersections of HI, right? So for all L being an m-1 intersection of the HIs, F restricted to L is consistent with a univariate polynomial. Of degree D. This is the local characterization. What this means for this complete m-dimensional complex, let me just do it for the case of m equals 3. When in m equals 3, we have all these t points down below. We have the t choose 2 things here, and finally we have the t choose 3 wise intersections. Then this corresponds to the 3 of them. It has sorry. The t things are the hyperplanes. These are the 2 wise intersections of them. These are the 3 wise intersections of them, which are all the points of the set. Okay, now let's take a particular edge, which is the intersection of 2 of them. You can complete it in many, many, many ways. T minus 2 ways roughly. So if these are consistent with the degree D polynomial, then then what it gives you is a candidate degree D polynomial for that particular line. Now, okay, now let's go to the two-dimensional the two-dimensional plane here. It contains within it many different. I mean, if you take a particular two-dimensional plane, you can intersect it with many other two-dimensional planes if it's living in three-dimensional space. What you will see on top of that plane is just a two-dimensional gap code, because if you take two-dimensional planes in 3D, which are in general position, and you fix one of those planes, then the remaining planes restricted to this particular plane will give you a bunch of lines in general position. And so it's a two-dimensional gap code. Okay, so what this gives us is decoding. I mean, so this gives us a local characterization. It also leads to a local test. The local test in the local testability sense. These are, of course, not far away from the C3 LTCs, but they are more in the spirit of Reed-Muller codes. They have similar testability to Reed-Muller codes. So this is a theorem that gap codes can achieve rate, any rate greater than less than 1, and local testability with n to the epsilon queries. This is also for any epsilon greater than 0. Yeah, and n is the length of the code. Okay, questions? How much time do I have left? -4. Okay, good. So my main open questions that I wanted to mention were, I've already said, which is, constructing better codes for better rate distance trade-offs for constant m, and also for large D and M to have constant rate codes. These are two main open questions. I will mention also one. So in the proof of this, the proof of this is similar to testability for Reed-Muller codes. Those of you in the school already saw some of the ideas. We saw proof of the local testability of Reed-Muller codes in the spirit of planes and general position, things like this. So you already saw some examples of that. Yeah, and inside this we have some other generalizations of the Polishchuk-Spielman statement, if you know what that means. Yeah, great. Thanks. Yeah. Yes, correct. And any R, yeah, local testability automatically comes with delta greater than 0. But yes, okay. Any R greater than 1 and some delta greater than 0. Yes. Yeah. Yes, these codes are decodable up to half their minimum distance. We give a simple decoder. Gap codes actually turn out to be much easier to decode than Reed-Muller codes themselves. There's a natural way in which you can view them as a concatenation of Reed-Solomon codes with Reed-Solomon codes, or maybe m times if it's an m-variate setting. So actually the decoders are just black box reinterpreting gap codes as a concatenated code and using known decoders. While for Reed-Muller codes, it's a much bigger struggle. So cap codes are not locally testable at all. Thanks for asking all the questions which I couldn't fit within the time. Yeah, so cap codes are not locally testable at all because they do not have many collinear point evaluation points. And so there's no chance of testing through that. And gap codes are distinct from them. We know because gap code would somehow have lots of collinear points inside. Yes, that's right. So I guess this is what a code on a complex means somehow. Yeah, and they're Tanner codes, but they achieve this, they have this property of being much better rate than what simple codimension counting gives. So usually you bound the rate of a Tanner code by saying, oh, we're imposing all these local codes everywhere and we're bounding the dimension by just some blind dimension counting. The fact that these Reed-Solomon codes that are sitting inside here are all aligned in a nice way with good interpretations, that's what's allowing the dimension to be much larger than what dimension counting would have given. Oh yes, okay. Yes. These are sheaf codes. Good. Okay. But it'll be great to find out what that means. Ah, I see. Oh, thanks.